It's often the case that we have a scenario where the acceleration is constant. There's also scenarios where acceleration is not constant, and so it's imperative that you evaluate what your situation is. But for things like free fall, the acceleration that you're experiencing as you fall down to Earth, the acceleration is constant. There are also problems that describe car traveling at constant acceleration, right? So it's moving with some increasing velocity, but its velocity is changing at a constant rate, and so the acceleration is constant. And so what we're going to do in this video is derive 4 equations that only apply to when there's constant acceleration. They are not always viable. So if you use them and your acceleration is changing, you'll get incorrect answers. But if your acceleration is constant, then you can use these 4 equations that we're going to derive to find out all kinds of missing variables that you might have. So if we start out with the fact that with constant acceleration, v acceleration is equal to a average. Right? Whatever the average acceleration is equal to the acceleration overall. And that is equal to, so if we're talking about a in the x direction, then ax is equal to the velocity in the x direction at point 2. Let's do this. At point 2 minus the velocity in the x direction at point 1 divided by t2 minus t1. Yeah? Well, if we set t1 equal to 0, t1 equal to 0, and t2 is any later time t, so t2 we're just going to call later time t, xv1, our v in the x direction at 1 is your initial velocity. We're going to call initial velocity is often written v naught. The little naught here refers to at time equals 0. You might also sometimes see it written v t equals 0, but more often you will see v naught, initial velocity. And velocity in the x direction at v2 is your ending velocity. We'll just call that your, we'll say ending velocity. Velocity. And we're going to call that v. And it's going to be velocity or v in the x direction at some time t that you're specifying. So end of velocity vx at some time t. So given all this, we can take our equation for acceleration up there and simplify it a little bit and say acceleration in the x direction is equal to vx minus v naught divided by t minus 0. And so you can solve for Vx, the velocity in the x direction, and we can make it as a function of time, yeah? Well, let me write it this way so I don't over-confuse what I'm doing. Vx is equal to the acceleration in the x direction times t plus v naught in the x direction. And so you see now that you can treat this as a function with respect to t. So v in the x direction as a function of time would be equal to ax t plus v naught in the x direction. So you can plug in some time value and get the Vx if you have the acceleration in the x direction, which is a constant, and your starting velocity, which is also a constant. So this is the first equation here. That you can use only when acceleration is constant. That's the only time, and I'll say it's equation 1 here. Only when acceleration is constant. All right, next equation. Let's go with a new color. Let's go with yellow. So constant acceleration, equation 2. Notice this first one, we were missing x. We don't know nor care what the final position was. We don't know what x was. That variable was missing. So if you come across a problem and it doesn't tell you anything about x, but it tells you about some of these quantities, that one might be appropriate. This next one that we're going to do, constant acceleration equation 2, is going to be missing Vx. This quantity here that has none of that in the equation. So we can do the same thought process for velocity and position that we did above for acceleration. So if we have v average in the x direction, v average in the x direction is equal to x minus x naught, right? Some later position minus the initial position divided by t, which you can think of as t2 minus t1, right? But if t1 is 0, then it's just t, right? And so what that works out to, or another way to express that, v average in the x direction is equal to v naught in the x direction plus Vx, the velocity in the x direction, divided by 2. Why can we say that? Well, if acceleration is constant, then velocity is some straight line. It's not curving. And so we can add initial and final, divide by 2, and get the average velocity that it's at. So if we take our first equation here that we came across, we take equation 1, and sub that into this Vx here, then we get V average in the x direction is equal to 1/2 axt plus 2 v naught in the x direction. Yeah. And then can simplify that to 1/2 axt plus v naught in the x direction. So this is an equation for v average in the x direction, and this is an equation for v average in the x direction as well. And so we can take those two and set them equal to each other. So we have the one above here, x minus x naught divided by t. We're going to set that equal to this guy here. It's equal to 1/2 ax t plus v naught x, because they're equivalent. They refer to the same quantity. And what we come out with, if we solve for x, is we get x is equal to 1/2 ax t squared plus v naught x t plus x naught. And this is our equation 2. So this is our equation 2. Move this all over a little. All right, and this is, again, you can see it's x. You can think of it as a function of t. So you can plug in various t values. Ax is constant, v naught x, the initial velocity, that's a constant, and your starting position is a constant. So you can plug in a t and get an x. Right? So this is our equation 2 for equations that are valid only when we have constant acceleration, but are very useful nonetheless. All right. And make everything small so that I can get my next page of notes here. All right, let's put this back up. Okay. Okay. So our next equation here, and you can see that. Next equation comes from solving equation 1 for t. There we go, we're finally set up. Sorry about that. So, new color. Let's go with this greenish color. Greenish bluish color. Alright. So we're going to solve equation 1 for t, and then substitute that in to equation 2. So if we solve equation 1 for t, t is equal to vx x minus v naught x divided by ax. Did I do that right? Alright, and then we're going to substitute that into equation 2. So, equation 2, right up above, we have x equal to, we have 1/2 ax, and then in for t, we're going to substitute all this. Vx minus v naught x over ax squared plus v naught x, and again all that for t, vx minus v naught x over ax plus x naught. All right, we're going to move this x naught over and multiply through by 2ax. And so you get 2ax, x minus x naught, equals vx minus v naught x squared plus 2 v naught x vx minus v naught x not squared. All right, which if you simplify a little bit, gets to vx squared minus 2 vx, oops, vx v naught x plus v naught x squared plus 2vx v naught x minus 2 v naught x squared. And this cancels with that, and we are left with, on the left side, we have we have 2ax, x minus x naught. And on the right side, we have very simply vx squared minus v naught x squared. And if we solve for vx squared, this one here, we solve for that guy, we have vx squared is equal to 2ax x minus x naught plus v naught x squared. And this is our equation 3. So maybe it's helpful, maybe it's not, to see where it comes from. If you're getting bogged down by what I'm doing and where all this is coming from, you can ignore it and just jot down the final equations here. But I think it's helpful to see where they come from. They don't just come out of nowhere. And you'll be applying these, not deriving them like I'm doing. So you don't ever have to worry about reproducing this. You could just use them and nothing else, and not worry about deriving them. All right, and now the last one. What color should we choose? We haven't gotten much blue in here. Let's go kind of a bluish here. The last one, oh yes, this equation has no time in it. There's no t in this equation. So the first one was velocity as a function of time. The next one was position as a function of time. Well, this one is neither. You know? This one has no time. Okay, so the fourth one here has no acceleration. So if the acceleration information is not given, nor do you need to solve for it, this may be your equation for the problem, if you need to do that. So we're going to start back with the two equations that we mentioned earlier. So we have V average, the x is equal to x minus x naught over t. And if acceleration is constant, then v average, the x direction, same quantity, is also equal to v naught x plus v x divided by 2. All right. So we can, you may have been wondering why we didn't do this earlier. We can just take these two and equate them and see what pops out. Yeah. So x, let's see if I can make a greater effort to stay within the same plane of writing here. X minus x naught divided by t, we're going to set equal to v naught x plus v x divided by 2. So you equate those, and we'll bring the t on over, and so you have x minus x naught is equal to, we'll write it like this, v naught x plus v x divided by 2 times t. And you can also write it, if your x naught is 0, you can think of this as x of t. It's a different equation for x of t, which doesn't include anything about acceleration. 1/2 v naught x plus 1 times t plus 1/2 v x times t. This is the same thing. We're just calling x naught 0, so the starting position is 0. But I'll label this as the official fourth equation. And box that on in. And these are the 4 equations that you can reference when you are doing problems that involve constant acceleration. All right. Next video, we will do a few examples that use these equations. So we're going to run through a few problems, at least a couple, that use these equations, and we can talk about methodology as to why we're choosing some equations versus others. Because when you have 4 equations and 4 or more quantities that we're talking about, it could be kind of confusing as to why you would use one or the other. And so we'll talk about that next video. All right, see you in the next video.